Well, so we are discussing this interval scheduling. Some greedy algorithms we are discussing. Okay. But the thing is that we started with this coin changing problem, and this is again this is from algorithm design textbook, Klinberg and Tardos, that is we very often call the KT book. Okay. And their slides and or Princeton course slide we are using. That already I have mentioned. Anyway, so in the previous class, what I have observed that in this we discussed this coin changing problem, okay, and little bit this interval scheduling problem, okay. But when I opened the recording, I have seen that okay, this recording is done properly, but somehow sound is not incorporated there. Sound is not there. Okay. So that's why I haven't uploaded it yet. Okay. But anyway, this coin changing problem is not so difficult problem. So I'll be uploading that also, that without sound one. But before going to this interval scheduling, as this is recorded without this sound, what I can do is I can just recap it very quickly, okay, so that in this lecture at least the salient points we can have here, okay. So I think you can remember this coin changing problem, okay. We are given some denominations like this, we are given some denominations, okay, and then this after getting this denomination we are given this $34 to be given back to the customer, okay. Then how many minimum number of coins will be needed for this? So that was the coin changing problem. And here we have seen, okay, the algorithm is at each iteration the coin of the largest value that does not take us past the amount to be paid we will be selecting, okay. So if 1, 5, 10, 25 and 100, and if $34 I have to pay back, then definitely I'll be first taking the largest value that is not taking us past 34, okay. And then we'll be subtracting how much is remaining, so 9, and then out of this denomination this 5 will be the next guy to be chosen, okay. And then 4 is remaining, and then we cannot do anything. Each time we have to choose one, okay. So these many number of coins necessary. And for this denomination, I have told you that for this denomination we can prove that this is optimal, but we have given some other examples where we have seen that this cashier's algorithm is not optimal at all, okay. So for the general conclusion is that the cashier's algorithm that we have designed, the greedy algorithm, that may not be optimal for some other denominations, US postage denomination, okay, like this. And if I have to give this 140, then we have seen, okay, this is not optimal. The cashier's algorithm will be choosing like this, but the optimal one is this, okay. Only two postages we have to use. And another bizarre example is that even it is not optimal, even the feasible solution also not possible at some point of time. So that is this 15 has to be matched up, but we are getting 9 first with the cashiers, and then from the remaining 8, so this 6, so we are seeing that no denominations available. But if we go by other algorithm, they might be choosing 7 and 8, and that will be with that $15 can be matched up, okay. So this was the overall idea of this cashier's algorithm, and this is a very good point regarding this greedy algorithm, this coin changing problem. We are seeing that greedy property. So the greedy property there. So the greedy property that we utilize there, greedy property, that is the largest value we are taking, which is not taking us past. So largest value we are taking. So this is the greediness we are choosing. We always choose the largest value, which is not taking us past that, the remaining one. Okay. And we have seen that, okay, this algorithm, the largest value, this is giving at some point of time some optimal algorithm, but in other cases this algorithm may not be optimal as well. So the general conclusion is that the greedy algorithm or the greedy heuristics we are choosing may not be optimal always. Okay, so may not be optimal always. That we have to remember. But whenever some optimality, say, we are sensing, then we definitely will be proving that. Okay, or at least we have to try to prove this, right? So one such algorithm that will be proving that greedy is giving optimal result, greedy algorithm, that is interval scheduling algorithm. And in the last class we have discussed what is this interval scheduling problem is. So we are having jobs which is having start time and finish time. Say this is 9 o'clock job, this is ending at 12 o'clock, something like this. And another job may be starting from say 10 and up to 1 o'clock it is running. Okay, so this type of overlapping jobs we might be thinking, so it is maybe 12:30 and then it is running up to 2:30, something like this. Okay, so given these jobs, then we have to schedule this job. We have to schedule this job in one resource that is available. One resource is available. So we have given one real life example that, okay, these jobs are the classes that will be taken by the faculty members. Okay, so somebody is telling, okay, 9 to 12, somebody is telling 10 to 1. They are trying to occupy this classroom. One resource is the classroom. Okay, so here classroom is the classroom. Here classroom is our this resource. Okay, and one classroom is there, and we have to schedule as many number of jobs as possible. Okay, so this is the problem that that we are facing within this interval scheduling, and how to go about this. Okay, so there might be several greedy templates that we can think of. Several greedy template. Okay, that means several greedy heuristics we can develop. Okay, we don't know which one will be giving the optimal solution. Okay, so say this is a template called this earliest start time template. Okay, consider jobs in ascending order of Sj. Okay, so if these jobs are given, right, if these jobs are given like this, say these are 3 jobs given. Okay, so consider jobs in ascending order of start time of the job. Okay, so here if we sort the jobs according to the start time, say this is job number 1, this is job number 2, this is job number 3. Okay, so if I consider the jobs in ascending order, can you tell me which job we will be taking first? Job number 1, 2 or 3. Ascending order of Sj. Which job? No. Ascending order of start time. 1. Yes. So start time. This is the first start time. Okay. If I sort the jobs based on start time, then this will be coming first, then this will be coming next, then this will be coming next. Okay. Right. So earliest start time, consider jobs in ascending order of Sj. So whichever is starting from the earliest start time, if I consider, then what will be happening? How we will be scheduling the jobs? Okay. So now, can you identify that if I do this, if I use these heuristics as a template, greedy template, always I am greedy in the sense that always I am starting with the jobs which is having the lowest start time. Okay. So that is the greediness here. And can you identify that if I do this, then can you configure one such scenario of the example that okay, we will be in trouble. We may not be able to schedule as many jobs as possible. In which case, can you identify this? Very easy. Okay. Yes, very good. Who is this guy? Very good. Absolutely beautiful answer. So this is the start time. So if this guy is the first one, okay, and it is having the longest duration, then what will be happening? Say that guy is taking from the event starting from 9 o'clock and it is up till 10 p.m. So this is 9 a.m. to 10 p.m. job, okay. Longest duration. So if I schedule this job, then no other job can be scheduled in that classroom according to our assumption. Okay. So only one job, if in the worst case, only one job can be scheduled if I take this template. Okay. And that is not at all we are achieving our optimality. Okay. So here we have shown that okay, the optimal result is not possible. Optimal result is not possible by taking one counter example. This is a very important term that we very often use in proving something that is not optimal. Okay, by giving some counter example, we are proving. Okay, but whenever we have to prove that it is optimal, then we have to give some other arguments. Okay, so we see. This is the counter example. This is the counter example for earliest start time, right? Earliest start time. So this guy is the culprit. This job is the culprit, right? So it is the longest. It is having the longest duration, right? And if I schedule this job, then you see no other jobs can be scheduled. Okay, all these jobs we cannot schedule in that classroom. But if I exclude this job by other algorithms, then I can easily accommodate all these jobs in that classroom. Okay, so this is a counter example which is eradicating the hope that okay, this earliest start time is going to be optimal. There is no hope that earliest start time template will be the optimal one. Okay. And the next template, okay, this earliest finish time, that will be coming afterwards. This shortest interval, okay, this shortest interval, consider jobs in ascending order of fj minus sj. That means which job having the smaller duration, that job. Then after the observation that, okay, this longest duration job might be happening in this start time first algorithm, then immediate reaction might be this, that, okay, this whichever is the shorter duration we should be using, we should be considering jobs, we should be sorting jobs according to that, and then in that order we will be considering the jobs. Okay, so even in that case we cannot achieve the optimal result. Okay, so here is the counter example. Okay, here is the counter example. So which job? So this is job number 1, this is job number 2, this is job number 3. Okay. Now can you tell me which is the job which is having the minimum interval? Okay, minimum interval. Which job having the minimum interval? 3. So if I schedule the job 3, then you see that job 3 is overlapping with this one and also overlapping with job 2. So I cannot schedule this guy and this guy here in this classroom 1. Okay, so classroom, in this classroom, so this classroom C. If I schedule 3, then I cannot schedule 1 and 2. But if some other algorithm is picking 1 first, then it can schedule 1. After completion of 1, it can schedule 2. Okay. So you see this start time, this shortest interval, if I consider by using shortest interval, then I can schedule only 1 job. But if I go by other examples, other algorithms, then maybe I can schedule 2 jobs. Okay, so definitely this shortest interval may not be the optimal one. Okay, so another template we can consider. Okay, so the template is fewest conflicts, right? So for each job J, count the number of conflicting jobs Cj it is having. So number of jobs it is conflicting with, and schedule in ascending order of that Cj. So how many jobs? If I am having lowest confliction, lowest number of confliction, then I may be selected earlier. Okay, so that is the idea. So this, if I select that template, then you see one counter example is given here. Okay. So you see this this guy having the fewest conflict. So this is having 1. It is conflicting with this guy and this guy, right? 2. And others, this guy, if I am considering this guy, how many? So this is conflicting with this and this is conflicting with all others. Okay. So like this way, this guy may be selected first. Okay, so now you see, if this guy, when this guy is selected, so it is already, I cannot select this guy and this guy, right? But some other algorithms, if some other algorithms are taken up, then I can take this guy, then this guy, then this guy, then this guy, I can take up. Okay, so this is the way that, okay, even the fewest conflict fast algorithm, that may not be optimal as well. Okay, so we are seeing that several greedy heuristics we are trying, but none of them so far is giving any hope that that will be leading to the optimal solution. Then what to do? Okay, is there any hope? Yes, there is a hope that if another template is still remaining. Okay, that might be leading to optimal solution. So that is the earliest finish time algorithm. Earliest finish time. So consider jobs in ascending order of finish time, FJ, right? So ascending order of finish time we have to consider, right? So if this guy, so in the template we had, so this is, if this is the case, okay, then you see this earliest finish time, that is giving what, right? So this which so I am numbering the jobs. So this is job number 1, this is job number 2, this is job number 3, right? And this is one finish time, and this is another finish time, and this is another finish time. So you have to sort the jobs according to the finish time. So now this, and then in that order I have to consider the jobs, and if they are compatible we have to consider the job in that classroom, okay, in that classroom. So now this according to our algorithm, so this guy is having the lowest finish time. So this we can sort it. 1 will be considered 1. Yes, 1, 3, 2, definitely. Very good. So 1, 3, 2, right. So this is the way we can schedule this, and then according to this order we have to consider the jobs. Okay, so first I am considering 1, and then no other job is considered, so I can schedule that job there in the classroom. And then I am selecting this guy, but this guy is having overlapping with this. Okay, so its finish time is more than the start time of this guy. Okay, so we cannot schedule this. So this guy we cannot schedule, incompatible job. And then if I consider 2, then its start time is more than the finish time of this. So there is no compatible issue. We can consider that job right now, and we can schedule that job. Okay. So you see, in this template we are not being able to schedule it optimally, but in this, if we consider this template earliest finish time, then definitely we are achieving the optimality. Okay, at least with the example we are getting that there is a sense of optimality there. Okay, so all these 4 templates, only hope is that earliest finish time. Okay, so the main idea of this earliest finish time is that, okay, what I am doing is earliest finish time, whichever job is finishing earlier, then I am considering this. Then that means whatever time is remaining for the rest of the jobs to be scheduled is becoming more. Okay, so that is the hope that, okay, this earliest finish time may be scheduling more number of jobs, because I am keeping longer duration for the remaining jobs, okay, to be scheduled. Okay, so here is the pseudocode of this earliest finish time. First, we are taking the inputs, number of jobs, start time, finish time. Okay, so sort the jobs by finish time, so that means we are sorting based on this finish time. So initially, the jobs which we are selecting, that will be stored in this array maybe, and for each job that I'll be considering, each job. So if job J is compatible with A, that means whatever jobs we have scheduled here, if job J is compatible with A, then we have to select that job and we have to put that into the array A along with the other jobs. And then finally we have to return that array A, okay, where we have stored the jobs. So this is the pseudocode of the algorithm, right? And whenever you will be asked to write the pseudocode, you should be writing like this, okay? You should be writing like this. So this, you use this arrow symbol, okay? Use this arrow symbol. Say if you are writing A equal A union this J, A union J, that means the job J being included in this A. That is not the standard notation, okay? You should be writing that A is becoming A union this J, okay? Something like this. So you should be writing like this, okay? Okay, now so this we can implement this earliest finish time first algorithm in order of n log n time, okay, in order of n log n time. So what we keep track of job J star that was added last to A, okay, so last to A. And if job J is compatible with A, if this start time of that job is greater than the finish time of the last job we are selecting, we selected, okay. So this guy is selected first, then this guy is selected, then who will be selected next, okay. So this guy, so this is the if J star, okay, and whose start time will be greater equals to, this is the SJ job that we're going to select next. Start time SJ will be greater equals to this, that job will be selected. So we don't have to compare this job with all other jobs. We have to select this job and we have to compare, okay. So with a constant number of comparisons we can do this. So what we are doing first we are doing that, okay, we are sorting the jobs based on finish time. That will be taking order of n log n time. Any standard sorting algorithm that will be giving you order of n log n time. Order of n log n time. And then each job how many jobs I am considering? N number of jobs. And each processing time will be taking order of 1 time. So this will be order of n again. So order of n log n plus order of n, so that will be order of n log. So n log n will be dominating. So the time complexity of this earliest finish time first algorithm will be this order of n log n, right? Okay. Okay. So now another thing, as I told you that, okay, this whenever we are dealing with this this sense that, okay, this greedy algorithm, this greedy template or this greedy algorithm by using this earliest finish time, we are sensing that it is going to be optimal. It is going to be optimal, or it is producing the optimal result, okay. Then how can we prove that this earliest finish time first algorithm is optimal, okay? So here the idea is that the idea will be greedy stays ahead. Greedy stays ahead algorithm, that will be that logic, sorry, not algorithm, greedy stays ahead. That idea we will be using, and the idea is that, okay, we will be thinking as a thought experiment. As a thought experiment, you think that you have designed the greedy template using this earliest finish time, and some other is telling, okay, I have developed one optimal algorithm. I have developed one optimal algorithm. Okay, so this is the algorithm, the greedy algorithm you have developed, and some other developed some optimal algorithm he or she is claiming. Okay, then you are telling, okay, on the same set of data, that means start time, finish time, jobs, somebody has provided or you have generated, and on the same input you are telling, okay, I will be running my greedy algorithm and another one will be running the optimal algorithm, and let's see what happens. Okay, right. So this is the idea, this idea as a thought experiment. The greedy algorithm you are running, that you have developed, and the other one is running any other algorithm. He or she is claiming, say, this is opt. So opt is running and greedy is running on the same input, right? And you are telling, okay, let us suppose that this up till ith iteration, whatever greedy has chosen, whatever jobs, the optimal algorithm has chosen that as well. Okay, so this is the greedy and this is the opt. So whatever greedy has chosen the jobs, the optimal algorithm has chosen the same jobs. Okay, now you see that this I plus 1th iteration, what will be happening? Okay, so according to the greedy algorithm, what the greedy algorithm will be choosing? Greedy algorithm will be choosing the jobs which are having the lowest finish time. Okay, so lowest finish time. So the greedy algorithm will be choosing a job which is having the lowest finish time. And now you see that if this guy opt, this algorithm, if it does anything other than the greedy, then it is choosing a job which is not the comprising the fact that it has chosen the lowest finish time. Then what will be happening? So greedy has chosen the lowest finish time, and you have chosen, or the opt has chosen some other jobs, okay, which is going beyond the finish time of this. So the remaining amount the greedy is preserving is more than the remaining amount the opt is preserving. So definitely this remaining portion can accommodate more number of jobs than the optimal one. So from here we can conclude that our greedy always stays ahead. Okay, our greedy algorithm always will be staying ahead based on the construction of this earliest finish time first algorithm. Okay, so this is the way you can prove. So this is proving the fact that, okay, this greedy algorithm is optimal. Okay, so greedy algorithm is optimal, so that it is proving. Okay, so this argument that, okay, up till some ith iteration both the greedy and the opt producing the same result, and then immediately after that iteration what is going to happen? Is greedy winning or greedy losing? So based on that fact, in many algorithms you can prove that, okay, your greedy algorithm will be definitely going to stay ahead with the others, and that argument will be giving the logic that greedy, in that case, greedy is giving the optimal solution. Okay, so today I think up to this, and in the next class we will be dealing with another algorithm that is called this interval partitioning. Okay, so this interval partitioning we will be using. So in this interval scheduling, we had one resource. That is one of the bottleneck. We had one resource. In interval partitioning, we will be having more resources. Okay, more than one resources. And what we can do, more than one resource, or it might be having as many resources as you want. Okay, so more number of resources we will be having, and in that case, what could be the scheduling problems that is being addressed by this interval partitioning algorithm, and that we can take in the next class. Okay, now if you have any question, then you can ask me right now. And all of you are implementing whatever algorithms I am discussing. Keep implementing that. Once upon a time, I mean, sometimes in the course I'll be one day I'll be fixing that who has done and who hasn't. Okay, so maybe beyond the class hours I can fix a time and I can check your assignments. Okay, so keep implementing that, right? Let me take your attendance. Why? I think less attendance today. I don't know why.